Swayam Prabha. Digital India. Educated India.
Welcome to the fourth lecture of the series on mineral resources. Just to have a small recapitulation, in the last class we were trying to rationalize the temporal distribution of mineral deposits, and in that we discussed the spectrum which gave the different mineral deposit types. They are basically called as the genetic types, and their occurrence in different time periods, and trying to find out what exactly they tell us. I would like to just go back to what we discussed, just one small a couple of points which I would like you to just again note. In addition to what we discussed about the relationship, or discussed about the correlated the occurrences or formation of these mineral deposits to the irreversible evolution of the hydrosphere atmosphere in terms of the oxidation state of the atmosphere. In addition to that, just some of the quick look we can have. Say for example, a deposit of lead, whichever deposit type we could consider, just as copper forms different genetic types, and so as lead in volcanogenic massive sulfide, in sediments and so on. But you see that lead deposits, there are no deposits which are older than about 1800 million years. Similarly, if you look at metals like tin, tungsten and molybdenum, they do their deposits also, if we consider them that is exactly what is real, then these deposits also formed only in the later part of the geologic history, mostly Mesozoic or post Mesozoic. These also need to be explained. One immediate or a very quick correlation which you could make here, if you remember, we were discussing about something called the enrichment factor, or the general crustal abundance of metals against the quantity that is available in terms of mineral deposits. We also discussed about something called enrichment factor. That means the number of times, or the order of magnitude by which one particular metal or an element has to be enriched to form its mineral deposit. And we observed that metals like tin, tungsten, molybdenum, they do have a very high value of the enrichment factor, and so as lead. So, without getting much into the intricacies, at least we can make one inference, quick inference here, that formation of deposits of scarce metals like molybdenum, tungsten, tin, which have a very high enrichment factor value of the order of 40,000, 60,000 or so. That means, it definitely took time, or it needed several cycles of such enrichment through normal rock forming or rock recycling processes to form their deposits. And there are many such observations we could make on this temporal spectrum, but these are some of the quick ones which we will be discussing them in details, which when we go to the individual genetic types. So, the present lecture is mostly here we are going to discuss about the attributes of the mineral deposits and try to give a general framework on basically on what several theories of ore deposit formation is based. As I have said before, this course is a first level course where we do not have much scope to delve much deeper into the subject of what we call as ore genesis, or the origin and evolution of the ore deposits, but what we only look at them in a very brief and conceptual manner without getting into much in the details of it. So, let us first try to see the attributes of these mineral deposits and what they are. First thing is that, which would look a little strange, but ore deposits are accidental in their occurrence in the crust. Why I say accidental? Because in the previous lecture we saw, and we also were quite convinced that the quantity of any metal present in its deposit is not actually in accordance with the equivalence or the similarity in the geological terrain across the continents of the world. So, if we get one deposit in a particular type of, say for example, we go to a granitic terrain in one particular continent, we get a deposit of say molybdenum, but that same situation where we go to another continent to a similar rock, similar granitic terrain, we may not get that deposit of molybdenum. A very simple way to reconcile it is that the deposit formation definitely requires a certain processes to have operated in a proper in a sequence proper in a required sequence, and to have operated to the optimal level. That will only give the result in a mineral deposit formation. And as of now, we have not been able to very precisely quantitatively understand these processes to put them in a deterministic manner, that yes, if we have such and such geological situation, we would expect to such and such mineral deposit to form. Even though we definitely attempt to make this science as exact as it be, but as it stands today, we are far from it. So, there is a element of chance which is there, that is the reason why we can also sometime use some probabilistic or stochastic model to predict the formation of these deposits, where it will be a semi empirical mixed with science and observation together. But then we also say that yet there is a method in the madness. So, when the mineral deposit formation looks like random or mad, but yet there is a method in the madness, when worked out, tells us exciting stories about evolution of the lithosphere, hydrosphere and atmosphere. We have just seen the formation of the iron deposits, older iron deposits, formation of uranium deposits, formation of certain deposits in much later in the geology history could be rationalized. So, there exists a parallelism between the formation of mineral deposits of different types and the evolution of the crust, continental crust, from the very beginning, the oldest to the present day. Ore deposits are distinct geological, physical and chemical entities in the crust and can also be called as anomalies in the crust. I will just try to explain what I mean by that. So, an ore body or an ore deposit, we have defined an ore deposit essentially has something which is called an ore body, which is an entity having a definite shape, size, I mean length, breadth and thickness in the associated with the crustal rock. Let us think of that we have a situation where this is a normal crustal rock. Now, in this normal crustal rock, let us say that there is a whatever may be its shape and size, we will look at them more closely when we look at the morphologies of different. Suppose this happens to be an ore body as you have defined. This is the common crustal rock. Let us say that this is a ore body of copper. So, what is basically meant as an anomaly or a, so this definitely is a distinct physical entity which is identifiable in a domain with respect to the surrounding rock, which basically we call as the country rock. So, what is meant by an anomaly is that the concentration of this particular metal such as copper has a value which is a threshold value or a Clark value of say 50 generally whatever it is, let me say it is 50 ppm. Anywhere within this rock I will get, wherever I analyze I will get a value of say 50 ppm or maybe within a little bit of an uncertainty. The moment I am taking a sample from this particular part, this is going to give me a much higher concentration, so let us say 1.5 weight percent. Or if I just try to plot, take different points and then try to plot, I will get something like this. So, that means the concentration of the metal is going to be maximum whenever I am going to measure the concentration from this. This actually is my ore body. So, that is why they are distinct physical chemical entities. They can be their shape, size and depth extension could be estimated by using various methods, and so that is how I can explain. And then these ore bodies. So, for example, this is a common rock and this is an ore. So, now there could be lots of questions which could be put here. When did this ore body come into existence and how it came into existence? There are so many questions. So, the next point which I have made here is as the attributes of mineral deposit is that they are a product of the earth's own mechanism of beneficiation. You all understand what beneficiation is. You all have studied in your school. One of the process of beneficiation which you all would have studied is the froth flotation process. In this froth flotation process, suppose I have an ore of a metal, say copper, where the percentage is 1.5 weight percent. This particular ore containing 1.5 weight percent of copper is not suitable to be taken into a processing plant or to taken into a plant where the ore could be subjected to some kind of a pyrometallurgical process such as a smelting to get the copper. Now, what is needed is that this particular material has to be improved in terms of its copper content to at least say 25 weight percent. Only when it becomes a material which is 25 weight percent by its concentration of the metal, then only it becomes suitable as per the present day technology to be taken into a smelter for extraction of the metal. Now, so then we need to have a process for increasing the metal content from this ore of 1.5 to 25 weight percent, and that is the process which we all know, that we crush the ore in a primary, secondary, tertiary crusher, take it to make a slurry and then make a froth and use the surface property of the, because this is very much dependent on what the presence of this metal in what form, in which mineral. So, that mineral's surface property is taken help of, and then the process is designed in such a way, if the mineral can be made into an aerophilic substance where they can be attached to bubbles, and those kind of bubbles can be formed by using a frother, and the rest of the process is well known to you. So, this is a process where we are designing a processing plant, it is man-made, a artificial process of beneficiation. So, similarly, whenever there is so if we say that in nature essentially the process is actually rock to ore. The way we have defined the rock, where the concentration of the metal is somewhere the threshold which is the Clark, and then this particular rock has to be enriched to form the ore. That is what is our enrichment process. So, that is why we say that this process, which can be obtained by a single step of enrichment or could be a multiple stage of enrichment, that is all done by nature, by the earth's own, whatever the endogenic and the exogenic processes that we have discussed have actually come into play to convert from a normal rock to an ore. And that normal rock could be anywhere, could be over there in the mantle, could be there in the lower crust, could be there in the upper crust, could be there on the surface, and where all the processes that we will be gradually discussing, like in a short while we will be going for the classes to see the classification. All these processes, either one of them or more than one of them in combination, would have acted to convert this particular rock to an ore. So, talk of magmatism. Magmatism is efficient in certain circumstances to convert from a rock to ore, that means through a melting process. Let us talk about weathering or erosion process, it is also capable. Let us talk about, so here it could be that either I could melt this rock and get the product where the concentration of a particular metal could be more. I could make this rock acted upon by a fluid, from where the essential the valuable metal content could be dissolved out and could be deposited in the form of where they could be enriched and will satisfy the criteria to be called as an ore. Or I could differentially leach out. Suppose if this is a rock and this contains certain metal in the form of its mineral, and where I would be able to get rid of all the constituents which are not necessary to me and can get it in the form of enriched form, which I can call it as an ore. So, all these, it could be a melting, it could be a action of fluid on that, it could be a process of weathering, erosion and transportation, it could be either one or a combination of one of them, which will act upon to convert a normal crustal rock to an ore. So, ore deposits are distributed non-uniformly in space and time, explainable on the changing nature of interaction of the lithosphere, hydrosphere, atmosphere, preservation of rocks of different geological time in the crust, which we have just justified, that the ore deposit formation can be visualized as a complex process of interaction of the lithosphere, hydrosphere and atmosphere. They can't be kept isolated from each other, in at least in relation to the formation of ore deposits of different types. And we also have just seen that whatever quantity of the metals that we see as our endowment of the total endowment of the continental crust with respect to consider any metal, any abundant metal or scarce metal, then they definitely are the amount that is left after any kind of a self destruction process, or what we get is actually the ones which are preserved. And there are some first order controls on their occurrence: the very chemical affinity of the metal, the form of the deposit, their abundance in the bulk earth, mantle, bulk crust, upper crust, and the mineralogical control. This we discussed in the very first introductory course, that the total quantity of the metal that is available to us is essentially controlled by the crustal abundance. What we see something is present in the crust today or in any ore body, we can always go back and see what is the ultimate source. Although we can just very crudely say that, well, the ultimate source is basically, first it starts with the solar nebula, then the formation of the bulk earth, from the bulk earth we had separation into core and mantle, and once the core is separated out, it is not involved in the process which is of interest to us as far as the ore deposit formation is concerned. So, then we will have a mantle and a continental crust formation. So, this is the stage 1, this is stage 2, this is stage 3, and then from this so now this is the core, this is the mantle, and this is this part is the crust, and this again goes to core, mantle, core, mantle, and this could be the lower crust and upper crust. We can always. So, this is the lower crust, this is the upper crust. So, ore deposit, so this could be a stage 4, and from stage 4 we do get the ores. So, that is our stage 5. So, at each step there is some enrichment that is taking place. Whatever the elements, they are getting fractionated between the solar nebula and the bulk earth. Elements or metals are getting fractionated during the core mantle formation. For example, any of the metals which are siderophile in their tendency, they have an affinity for iron, will like platinum group of metal, gold, they will go into the core and not be available in that much quantity to form ore. Then during the crust and mantle fractionation, most of the elements which are lithophile, they will be enriched in the crust, and then the lower crust and upper crust fractionation will further take place, and whatever we get as ore deposits are further enrichment process from the upper crust. So, there can happen in just one stage of enrichment or multiple stages of enrichment, depending on what is the abundance of that particular metal in the upper crust and what is the enrichment factor that it would require. And also we discussed that the availability of any particular metal in the quantity that we have them is essentially controlled by fundamental parameters, like whether they are present in their discrete mineral phase or not, because it will be sometimes will be easier if that particular metal is present in its discrete mineral phase. It will be easy for us to extract it, separate it out and get the metal out of it, or use the mineral if it can be used directly as a raw material. And compared to a situation where the metal remains as in trace quantity in common rock, and that becomes difficult for that particular metal to be extracted out. The very good example here is the germanium and molybdenum. Germanium and molybdenum have near identical abundance in the crust, but the total amount of molybdenum available to us in the form of deposit is far more than the total amount that is available to us for germanium, because germanium is a lithophile element and remains in the lattices of the silicate minerals, whereas molybdenum is a chalcophile element, forms its sulphide very readily, and that is how we can recover them in larger quantity whenever it forms an ore body. So, we have seen that the ore deposit formation are correlatable to broad earth processes, magmatism, sedimentation, metamorphism, driven by the endogenous and exogenous processes under diverse tectonic environments. So, tectonism is always the operative force, and under diverse tectonic environments, thus providing a broad framework for classification of ore deposits. We will see how we can classify them. This also emphasizes the importance of the understanding of the behavior of elements in different environments. So, we can always think of the formation of a mineral deposit of any particular metal coming out of processes which can be very well defined in their domains. For example, if we are talking about magmatism, then it is a domain of solid and melt interaction. So, any of the metal or element to be enriched, their behavior will be depending on the energetics, on their fractionation in a solid melt system. It could be a situation, it could be melt, means one of the melt component can get fractionated out from a parent melt, and if that also involves fractionation or enrichment of any of the particular metal or metals, that becomes a process. It could be a melt and fluid, it could be fluid, melt and fluid situation we will see, it could be fluid, it could be fluid and solid. And deposits are primarily characterized by their mineralogy. So, mineralogy is a very essential attribute of any mineral deposit. So, the first and foremost, as we all being geologists, the very first and foremost attribute of a mineral deposit, of an ore body to be very specific, or the mineral or the mineralogy. So, mineralogy is essentially we understand what are the minerals which are present there. In the introductory course lecture, we saw the we all know the mineral kingdom's division into silicates and non-silicates. These non-silicates are all oxides, sulfides, carbonates and so on. So, what is essentially required is that we must identify what is the mineral that is present in an ore body, mineral 1, mineral 2 and so on, mineral n, because this gives us the first hand information, because minerals, as we stated earlier, a mineral a metal which is occurring in its oxide form or sulfide form or sulphate or carbonate or so this is very much controlled by chemistry, by the physicochemical environment in which the ore body is forming. So, understanding the mineral is or getting the minerals is very important. We do have laboratory methods to, we are all very familiar with seeing thin sections of rocks and identifying minerals. Some of the basic difference between the minerals which occur in silicates and minerals of some of the metals which either occur as oxides or sulfides, which are generally opaque to ordinary light, they are also studied by making some sections from them, and they are studied under incident light. And the first and foremost exercise that in any study of an ore deposit is to characterize the ore deposit in terms of its mineralogy. So, what exactly briefly we can see, we can discuss them in greater details later. Suppose there is an ore body where there are minerals M1, M2, M3 and so on up to Mn. Now, what generally is required for us to understand is that whether, how and when these minerals formed, whether they formed as mineral assemblages in different points of time, and if so, then whether it is possible to work them out. So, this is the first step that we follow, that to understand something called the paragenetic sequence. Suppose there are M4 and M5, M6 and M7. There are 7 minerals that I am finding in an ore body, in an ore, sample of ore. So, here I could represent it in terms of a qualitative sense in time, not in absolute sense, but in qualitative sense, in relative sense, early, late and so on, and I can represent them in situations like this. And say for example, M1 was here, M2 was here, M3 was here. So, by looking at the mutual intergrowth, I could just show you some of the quick So, these are some of the photographs, photomicrographs that we have that I could show you here. Here it is an example where you see that this is Py is for pyrite, this is for pyrrhotite is FeS. Pyrrhotite is also iron sulfide. This is what essentially could be thought of as a mineral assemblage. Here we are seeing that there are 2 minerals. In this case, we find that there are more than 2 minerals. This is pyrite, this is fullerite, this is tetrahedrite, galena. These are forming a mineral. This was what exactly we mean by an assemblage. And by looking at these kind of photograph, these kind of images, you see that if here there are 2 minerals which are present, this is quite different from the situation which is depicted here. This is a pyrrhotite and a pentalendite, which is nickel sulfide, and this is iron sulfide. In this case, it is these needles are essentially of ilmenite within the main bulk of the material, which is magnetite. So, even though we will we exactly are not going to understand what they are, but it is very easy to see that this mutual intergrowth of these minerals depicted in these 3 or 4 diagrams are different. They represent certain different processes. So, these different processes can be essentially thought of if we say that we are trying to understand the ore texture, then this ore texture could result from a primary growth of these minerals together. They could be monomineralic or they could be polymineralic, they could crystallize from a melt or precipitation from fluid. There could be secondary reaction, replacement, reaction relation, replacement, alteration, deformation, exsolution, annealing and fluid assisted replacement and so on and so forth. So, these are all the processes that we can think of in that are interpretable by studying the ore minerals. When more than one ore minerals are present, we can see from the way they are intergrown with each other, and so we will continue discussing in the next lecture. Thank you for today. We will continue in the next lecture.